problem we're looking at now is what's known as a vertical sextant angle. We use a vertical sextant angle when we wish to calculate how far we are off lighthouse or land, for example. The height of lighthouses are given on the chart, and they're also given in the Admiralty list of lights. And this height is measured from mean high water springs to the centre of the lantern in the lighthouse. Of course, it'll be pretty rare that they will be at this height, because it's not often that the tide is at mean high water springs. But it's not so much of a problem when we're calculating by a vertical sextant angle, because if the height is different, in reality we'll actually be further away than we think we are from the lighthouse. So it's better to be further away than closer. So we know the height of the lighthouse. We've measured by vertical sextant angle the height from the vessel, and with these two values, let's see if we can calculate our actual distance off the lighthouse. Okay, well, we can solve this mathematically, because with the right angle triangle that we have here, the side opposite the angle is mean high water springs. The side adjacent to the angle is our distance off. And we know that opposite over adjacent is tangent. Therefore, tangent of theta, or the angle that we've measured here, opposite over adjacent is mean high water springs, height of the lighthouse, divided by the distance off. So if we transpose the formula, we know that distance off is mean high water springs, the height of the lighthouse, divided by tangent of theta. So we've got an example here that we've worked out, and we've assumed that the height of the lighthouse is 70 metres, and we've assumed that the vertical sextant angle that we obtained was 1 degree 05 minutes. So we've got 1 degree 05 and a height there of 70 metres. So by calculation, 70 metres divided by tangent of 105 gives us 3,702 metres. We need to convert that to nautical miles, and we know that there's 1,852 metres in 1 nautical mile. Therefore, divide our height there, well, our total 3,702 metres, divided by 1852, and that gives us a distance off of 1.998 nautical miles. So you can see mathematically we can solve the problem providing we've got the height of the lighthouse and we've measured our angle vertically with our sextant. We can also obtain this information from Norris nautical tables. So we can obtain the information from Norris, and it's on page, starting on page 510, distance by vertical angle. Okay, so let's look it up in the tables. We know that our height of our object, the lighthouse, was 70 metres. So along the top, height of object 70 metres. Be careful you don't mix up metres and feet. So our height of the object was 70. The column in here is degrees and minutes. So these are the vertical sextant angles. So let's go down at 70 metres, which was the height of the object, down to 1 degree 05, which was our angle. Once we've reached that, we go across to the column on the left, and we find that the distance in miles off is exactly 2 miles. So 70 metres height down to 1 degree 05 gives us 2 miles. And if we look at the answer we obtained, we had 1.998 nautical miles, so 2 miles. So you can see you can solve the problem either mathematically or using the tables. Also, if you wish to maintain a certain distance off a lighthouse and you knew its height, then you could calculate what angle to keep your sextant at, and as long as the vessel maintained that angle, you'd be that distance off the object. Now in this instance, let's say the height of the object, the lighthouse, was 55 metres, and we wish to be 2.5 miles off the lighthouse at all times. So let's go down the 55 metre column until we get to 2.5 miles, go across, and that tells us that our sextant, our vertical angle of the sextant, needs to be maintained at 0 degrees 41 minutes. As long as it's 0 degrees 41 minutes, we will be 2.5 miles off that lighthouse. And that's often referred to as a vertical danger angle. So in other words, if we can keep that angle, we'll keep ourselves out of danger.